Welcome to Module 11 and Chapter 25. This is our last new chapter of the semester. And in it, we're going to be looking at some statistics and how to use statistics to make decisions and to characterize our data, our variables, your design components. And the term statistic is used to denote a quantity of a sample. Examples include a sample mean, a sample variance, a sample quantile value. Statistics are themselves random variables, and we're going to need to treat them as random variables in order to make some of the assertions and use them in the way we will in this chapter. Statistics can be used to estimate parameters of a distribution, and we do that all the time when we describe the mean, the variance, the standard deviation of a sample and use it to make assertions about a population. In 25.2, because 25.1 is very slim and 25.2 isn't very heavy either, but in 25.2 we're going to look at point estimates of a parameter. These can seem overly complicated when they're actually very straightforward. A point estimate of an unknown parameter is a statistic that represents a best guess or best estimate uh, um, at uh, at the value of the parameter. So you're trying to predict what the parameter is for the population, and we do that based on observations collected in a sample. There may be one or more sensible point estimate for a parameter, and the estimated parameter is designated by a hat symbol typically. Thus, if we have a parameter theta, our estimate would be theta hat. The most obvious example of a point estimate is the parameter um, mu, and it's very commonly estimated as the sample mean. So if we want a population mean, we'll often take a sample mean, x bar, and say our best estimate of the population mean is our sample mean. And that's really a straightforward thing, and we shouldn't make it too complicated. So coming up with a point estimate is a relatively straightforward task. When we go through the task of trying to identify an unbiased point estimate, a point estimate is said to be unbiased if the expected value of the point estimate is equal to the true value of the parameter. Remember, the expected value is what we know that we would need to expect given enough observations. We're going to know the value that we should expect. If there's any the amount of any bias is defined as the expected value of our estimate minus the true population parameter. So that would, if we have a sampling technique that has bias in it, we would have an actual difference between our expected value for the parameter and the population parameter that lies underneath it. When we're looking for point estimates of a population mean or variance, we want to get those values mu and sigma squared. And if we have a number of observations, x1, x2, all the way to xn, we can make point estimates of the statistics that we want and use the parameters that came from our sample to estimate those same parameters of the population. Thus, our best estimate for the population mean is x bar, and our best estimate for the sigma squared, or the sample of the population variance, is the sample variance. So these are straightforward things, and we shouldn't make them overly complicated.